Uh, and welcome everyone to the Winds and Currents webinar. Today, we're fortunate to have Roger Samelson from Oregon State University, who's going to talk about wind drift in a homogeneous equilibrium sea.
Okay.
So I'll let you go ahead, Roger.
Thank you, Sarah. And thanks for having me in this series. It's been a really interesting series so far, and I'm looking forward to more of it. So I wanted to try to explain some ideas that went into a paper that appeared in JPO just recently. And as Ernesto was just mentioning, I wanted to give some motivation here, which actually comes from the Doppler scatterometry, from looking forward to the Odyssey mission and to looking at Doppler scat. And it's really an exciting possibility that we may have global measurements of total surface ocean current from satellite remote sensing in the future. So it's an exciting development. And one aspect of it, about 5 years ago or so, I think it was, that I started to become aware of this possibility. And my understanding at that time, the Doppler scatterometry is in the Ka band, so it has centimeter scale Bragg scattering at the surface. And so the initial expectation was that actually it might be the very near surface current that it would sense, in other words, within a centimeter or so of the surface. And this brought back to mind some old ideas about oil spill modeling, mostly that the surface current is actually at 3% of the wind speed and 15 degrees to the right of the wind. This is something I heard first from Jim O'Brien almost 40 years ago now at a workshop in a little town close to Barcelona on the French side of the border. And this goes back to work in the 50s by Coiligan and Van Dorn and others after that, and continues to be an important part of oil spill modeling. The Zelenki reference there is to the NOAA operational manual for how to model oil spills. And if you think about that 3% at 7 meters per second wind, that's 20 centimeters per second. So it's comparable to mesoscale geostrophic currents. So overall, the idea that understanding this near surface wind drift will be important, both for recalibration of the retrievals and for physical interpretation of the measurements of Doppler scat, the airborne version that is now flying in S mode and other experiments, and the future Odyssey. It really is what started me to think about this problem. Now, present understanding is actually that the measurement, and Ernesto could comment on this with much more understanding than I have, that there's an effective average of something like the upper meter of the surface current, and this is because the Bragg scatters turn out actually to be bound to the larger scale gravity waves. But the 1 meter depth it probably reduces, as you'll see in this model at least, the response to about 1%, but it's still significant. It's still something that we need to try to understand. So if these movies work, I have a couple of short videos just to introduce the subject. This one is from Andrei Sherbina, and if you look at both the white specks that are sitting on the surface and this sort of drogued biological piece of material here that extends a little deeper in the water column, you can see the very near shear layer in this movie, the differential motion of the specks and that slower moving object. Okay, so of course that's not the ocean, and if I can manage to get to the next page here, and if this movie works too, this is the sail drone that went into the hurricane. And of course, the actual sea surface looks a little bit different most of the time. Though some of the time it looks like the first movie. Things are most of the time somewhat in between here. So what I want to try to do here is propose what I think is a plausible dynamical model of the mean wind and wind wave drift currents in the upper few meters, just the upper few meters of the water column, under statistically homogeneous equilibrium conditions. You might think of this as sort of an ocean counterpart to the mean neutral wind profile that we think of and have for decades as being implicit in the bulk wind stress algorithms. So first of all, the question of the homogeneous equilibrium sea assumption here. What I mean is, first of all, there are no horizontal or temporal gradients in mean properties of wave or current fields. and also that the ocean and the atmosphere above it, for that matter, have uniform density, neutral stability, so there's no air-sea exchange of heat or mass or anything like that. In addition, just to specify this even more so, the wave field is in equilibrium with the wind, and so all the air-sea momentum flux goes into the mean field. If it goes into the wave, it comes back out of the waves. And so from that point of view, one can view all the mean motion, including any Stokes drift, as wind drift. And if you think about that, you would expect on very general physical grounds that there would be some unique current profile for any given wind speed. There really isn't any other variation left. Maybe there's a bit of latitudinal exception to that. So the idea of wind wave equilibrium, of course, it seems like it's a reasonable starting point from a theoretical point of view anyway, but there's actually evidence that it's fairly frequent in the ocean. The number one here, and the figure comes from the Edson et al. Core 3.5 bulk flux algorithm paper. And what you see there is the relation that they found in the calibration data for that bulk flux algorithm between the wave age and the 10-meter neutral wind speed. And the wave age is the air friction velocity divided by a phase speed representing something like the peak of the wave spectrum. So you can see let's see if I have a pointer, the relation here with the solid line and the data points with the indication of the spread around that basically for this data set at each wind speed, there's a unique wave age. And that essentially means that there is an equilibrium or some sort of quasi-equilibrium, at least in this data set. An old classical assumption is that what you need for equilibrium is so-called fully developed seas equilibrium is a constant wave age, and they've plotted that, and here's the dashed line that runs across, and there are different values for this. The one that I ended up using is an older one. It's not too important exactly what it is. And there are other evidences from direct wave observations that this is a frequent occurrence, that wind waves are frequently close to equilibrium. And of course, as Tom Farrar pointed out to me, the Beaufort wind scale in its current version wouldn't work very well since it relies on the wave state to sort of give an evidence for what the winds are. So eventually here, I'm going to use two models of the wave state, and one of them is associated with this bulk flux, what I call the bulk flux wave state, and one is the fully developed seas wave state. But the main point here is just that I'm going to consider the case where these things are in equilibrium. So here's sort of a summary of where we are so far. I want this simple model of the mean wind and wave drift in the upper few meters. So it's not a boundary layer model, it's really just the upper few meters. There are no heat fluxes, precipitation, evaporation, or stratification. Everything is homogeneous and stationary. The wave state's in equilibrium. Think about that. Really, the only thing you can get for the mean momentum balance is the old classical balance of Coriolis force with a vertical stress divergence. And here, of course, we're away from the equator. So, but there are some questions here, namely what exactly, so we know what the density is and we know what the Coriolis parameter is, but we don't know so well necessarily exactly what we mean by the velocity, or even by the stress, or maybe even by the vertical depth variable there, because we need to consider an average that's going to maintain a sharp interface at say the point z equals 0 at some fixed z, or else this equation doesn't really make sense in the upper few meters. We would also like to get a momentum balance that keeps the total mean parcel motion in u, and that way we don't have to worry about adding in the Stokes-Coriolis force afterwards, or whether the turbulence feels the wave drift shear or anything like that. It's just basically sort of incorporated from the beginning. So here's the way that I propose to do that. It's basically a mass-weighted mean, and I argue that this captures the total mean parcel motion. And the main thing is we need to maintain that sharp interface at the surface. And so if you compute the means, I see I have an extra preposition in there, but we compute the means on surfaces of constant pseudo-vertical coordinate in a surface-conforming curvilinear coordinate system, then we catch these things. So basically the first equation there, we take a volume integral of some quantity we're interested in, and we use a Dirac delta to specify the surface of constant pseudo-vertical coordinate eta. So that would be eta naught there, that constant value. And then we compute that integral. So for the uniform density fluid, since it's a volume integral, it's a mass-weighted spatial mean. To evaluate this, we need to change variables so that we do the right thing with the Dirac delta. And in the course of that, we pick up a Jacobian here, this J term, which is the transformation between the original Cartesian coordinates and the surface conforming curvilinear coordinates. And then we can compute a time mean of this mass-weighted spatial mean as well. So just a little bit more of the fine print here. We have this mass-weighted spatial mean at the top in its original formulation. We do the transformation, so we get this Jacobian, and this Jacobian turns out to be, well, as I said, it's a mass weighting. And even though the fluid is incompressible, in the surface, the transformation to the surface conforming coordinates is not, it doesn't preserve that compressibility, so the fluid is effectively compressible in that coordinate system. And last point here at the bottom, if you integrate the resulting area average on that surface over the vertical, you recover the total mean momentum, and that's only because the Jacobian is in there. If you don't have the Jacobian, then you don't recover it. So just a sort of visual illustration of the sort of compressibility in that coordinate system. So we have Cartesian coordinates as the axis labels and coordinates, and then sort of a free surface deformation in the thick blue line at the top, and then the coordinates in the red and the blue. And you can see up at the upper left where the free surface is raised, the coordinate box there in the compressible curvilinear coordinates is a little bit larger than the one in the center at the top. And that is the effective compressibility of the fluid in this transformation. So there's basically a little bit more mass in that. The density is constant in the physical space, but it's compressible in the curvilinear coordinates. So there's a little bit more mass in the big box up at the top left than the little box in the center top. So the result of this is if you go through and compute the classical linear sinusoidal wave Stokes drift, rather, if you compute this mean for the classical linear sinusoidal waves, you do pick up the Stokes drift. And I don't want to go through calculation here, but the details are there. And a couple of notes. If you specialize to small wave slopes, then you can interpret this mass-weighted mean as a thickness-weighted mean in the original horizontal Cartesian coordinate. If you leave out the Jacobian, you get something that's like the Pollard result, where you only get half the Stokes drift. Another note here is if you look at Gerstner waves or Pollard-Gerstner waves, which have no Stokes drift, you get the right answers in that case as well. So this is evidence that this mass-weighted mean does pick up the total mean parcel motion. And maybe that's a surprise, but maybe it shouldn't be a surprise. If you look at the fixed depth Eulerian mean for linear sinusoidal waves, actually do capture all the wave drift. You just place it all above the wave trough. So here's a couple of means in the green and the blue. The green is the Eulerian versus depth. And the wave trough is just a little bit below zero here in this normalized coordinate system. And you can see the big jet effectively of Eulerian momentum that the fixed depth mean captures, but it places it all above the trough. And if you use the mass-weighted mean, or you compute the Stokes drift with the standard Lagrangian approach, you get this mass-weighted, you get the blue curve instead. Those two end up agreeing. So we come back to this mean horizontal momentum balance, and it looks the same as before, but we have a little bit different understanding of what it means in this case, so to speak. So now we interpret U as the mass-weighted mean, and just the deviation from the geostrophic mean, of course, is what I'm talking about, but it includes all the wave effects, including any wave drift terms that might give a Stokes Coriolis force, that sort of thing. And the stress is an effective mean stress. It's computed from the mass-weighted mean of the stress divergence, and there are a few other small terms in there as well, but I'm going to end up parameterizing it anyway, so it doesn't much matter. So I integrate those means. Oops, sorry, every time I move the mouse, it changes slides here. And I'm back one. And the mass-weighted mean of the depth of the surface of constant pseudo-vertical coordinate is what we now take for the depth here, and that is only a second-order effect as well. So this is basically the same as the original depth, Cartesian depth. So I have in the Odyssey theme here, I have a short quote from Joyce's retelling of the Odyssey. Longest way around, it's the shortest way home, which I think is so coming back to this familiar momentum balance, but with a little bit different picture of what it means. It's an old proverb, I think. So now we come to the closure assumption here, and this is pretty classical, right? We take the effective mean stress and we parameterize it in terms of an eddy viscosity times the mean shear. And the eddy viscosity looks a lot like the classical sort of law of the wall type form. So it has a roughness length of Z0, and it has a dependence that increases, so Z is increasing downward negatively. So the term on the far right of AV is growing in positive values as you get away from the surface. Then there's U star, the friction velocity, and kappa, the von Karman constant. Then there is also a wave effect parameter, and the effect of that is essentially to change the von Karman constant. So what it means is we allow the turbulent eddies, in effect, to grow at a different rate away from the surface than they would if this were a rigid wall boundary layer. So this is analogous to the stability functions in atmospheric similarity theory, Mononovikov similarity theory for the atmospheric boundary layer. But in this case, I just make it a constant. I don't try to make it dependent on any scale depth. But both those constants now, the roughness length, the Z0, and the wave effect parameter phi W are going to depend upon the wind speed. That's the essential assumption here. Now, this equation goes back quite a ways. It has analytical solutions in terms of modified Bessel functions that go back to Ellison. And Blackadar and Tenikis then sort of did this by asymptotics without apparently being aware of Ellison's work, and actually find this description of the possible description of the ocean boundary layer in these terms in the Tenikis and Lumley turbulence book in 1972. That's the first sort of place I've found it. But the main novelty here is that wave effect parameter. So this just says all these things again. There's the summary of the model formulation. We have the traditional equations, and we have this eddy turbulence closure that includes the wave effect parameter as the main novelty there. So a couple of details at the bottom. Actually make a piecewise linear extension of this to prevent the unbounded increase with depth. It's not too important, but it is more realistic. It has, then you also get complex exponentials, as in the classical Ekman layer case in the points of at which, for the regions at which the eddy viscosity is actually constant with depth. And now the question of the calibration. And so what I do for this calibration is pull together two things. I don't feel that the data are really adequate, or I didn't feel that at this point to try to do this directly. And so instead, it seems to me there's a lot of evidence of various sorts that the Stokes drift profiles say something significant and important about what the drift is actually near the sea surface. So I take those as a prediction of what it should be. In other words, sort of take them at face value as an estimate of what the drift actually is, and use that to constrain the mean shear and something about the dependence of the mean shear with on the 10-meter neutral wind through the assumption of the equilibrium wave state. Then also at the surface, then in a few instances, especially for low wind speeds, I impose this 3% rule or something like it. So the result of this is profiles, say of the upper 10 meters here, of the uh, estimated Stokes drift in the red for either the bulk flux wave state, which are the top panels, or the fully developed C wave state, which are the lower panels, and either a monochromatic estimate, which are the solid lines, or a spectral estimate, which are the dashed lines. Plus the green dot there is giving you an indication of where the 3% value would be. And so where those are quite a bit larger than the Stokes drift estimates would be, I continue to impose that 3% rule. And you can see the main difference between the monochromatic and the spectral wave states is that there's more shear near the surface for the spectral estimates because you get the shorter wavelengths, and so less penetration with depth of the Stokes drift that comes out of that. Then the blue lines are sort of model fits based on guesses at what those parameters should be, or fitting, not in a formal way, but as best I could, fitting the blue curves to the red curves effectively. So here is what the parameters come out. Here's how they come out. And so I have the closure equation at the top there, and on the left is the roughness length, on the right, in the center, the wave effect parameter, and on the right, the surface value of the eddy viscosity, which is just the wave effect parameter times the Von-Karman constant, the friction velocity, and the roughness length. And you can see on the left that with 10-meter wind speed increasing up to 20 meters per second, that the roughness length goes from sort of the very skin values, sort of similar to atmospheric drag coefficient roughness lengths, up to order meters or more. And at the same time, the wave effect parameter actually decreases by an order of magnitude from near 1, which would be the rigid boundary layer value, a rigid wall boundary layer value, to about 0.1 at the highest wind speeds considered here. And the result of that is that the eddy viscosity also changes by many orders of magnitude, the surface value, so that at the lowest wind speeds, it's basically even less than molecular viscosity. So there's a viscous sublayer implied. The molecular viscosity is the dashed line there on the right, and the black dashed or dotted line, all the way up to values of order 10 to the minus 2 meters squared per second or so for the higher wind speeds. So what then do the drift velocity profiles look like when you put these parameters into the model? And here's a way of looking at those. On the top panel is the magnitude of the model velocity versus wind speed at various depths, so 0, 1, 2, 5, and 10 meters, going from the thick solid down to the dotted blue line. And in the bottom two panels is the direction at those depths versus wind speed again. And the left panel is the calibration based on the monochromatic Stokes drift, and the right panel is spectral Stokes drift. And so you can see there's a little bit more shear near the surface, particularly at the higher wind speeds in the calibration on the right. And on the whole, so the red lines are the 3% rule, 15 degrees. And you can see actually the surface velocity is fairly close to that in all cases, but by the time you get to 1 meter, there's a significant amount of shear in both of those, and they're quite far below that. And similarly, the surface velocity is somewhere near 15 degrees to the right of the wind out to about 10 meters per second or so, and then it gets closer to the Ekman value of 45 degrees, which is the dotted line in the lower panels, but it never gets past about 35 degrees or so, or less for the spectral calibration. So this gives you sort of one picture of what the model suggests. Here's another picture. There's probably too much information in this plot, but you can look at the velocity magnitude, the shear magnitude, the angle, the friction velocity, the stress angle, and the dissipation, which is only the mean flow dissipation here, as a function of depth and wind speed. And I'm going to come back to I'm not going to say too much about this, but I'll come back to the bottom plots eventually here for a moment. So now just looking at the model and thinking more schematically and about regimes based on those the past two slides, maybe this is a little bit easier way to recognize what's in those plots. And so the idea here is as a function of wind speed and depth, and the upper panels are linear depth and the lower panels are log 10 depth, there are regimes in this model. And first, there is a constant stress log layer, but it's very shallow. It's only a few tens of centimeters, which is basically what one would expect by comparison of the depth of the atmospheric log layer, which is, of order 10 meters or so. So it should be about 1/30th of that based on the square root of density ratio scaling. And that's where it turns out to be in this model. And only for wind speeds of under 10 meters per second or so. Above that, there's something that really is more of a constant shear layer because the eddy viscosity gets so large. Then below that, down to some depth of several meters, there's considerable rotation in the velocity, but the downwind velocity continues to be quasi-logarithmic. So there's something that sort of looks a little bit log layer-like, but it's really rotated. It's not a constant stress layer in the classical sense. And then at greater depth, there's something that looks more like a quasi-Ekman layer. And of course, here the model becomes less interesting because it doesn't contain stratification or all these other elements that we know are important for boundary layer models. So now I want to come back to, as I said, I was going to come back to that dissipation model. There is a way of thinking about this roughness length in terms of wave breaking dissipation. So I wanted to mention that. If you consider defining a wave breaking turbulence velocity and length scale as 3 times u star, and the length scale being a third of the sort of completely empirical roughness length, then the implied TKE, the wave turbulence kinetic energy, and the wave dissipation scales that you get from that will be about 1 and 2 orders of magnitude respectively greater than the mean shear turbulence kinetic energy and dissipation, which is in the right ballpark for the wave dissipation. But of course, if you take the product of these, you get the same surface value of the eddy viscosity. So that's the reason for multiplying one by 3 and dividing the other by 3. So the test here is, does the wave breaking length scale that you get out of this, the ZW, is it comparable to the observed depth of the wave breaking layer? And for that, the roughness length has to end up being sort of close to the significant wave height. And so here I'm coming back to that bottom panel that I showed you before. And the dashed white line, not the dotted one, but the dashed white line near the surface, is a third of this roughness length. And the 1/3 of the 2 estimates of wave state are the solid red lines. So you can see they don't match up exactly, but especially towards the higher wind speeds, they're in the same ballpark. So this interpretation seems to have some consistency to it. So I've done just a very preliminary comparison of the model to the existing observations, and there's sort of been an explosion of these observations in the last few years, and I have not yet done that comparison. So this is with some more classical results. The 3 on the left are drifter results from Churchill and Gennady, and then from Kudryavtsev, and then one set of more recent ones from Mori et al. From the Gulf of Mexico. These don't, so in the 2 left panels, the boxes are the observations and the lines are the model. There's actually not a very strong relation in the data here between wind speed and the shear, or that's actually shown here. So the model goes sort of through the cloud of observations, but so it's sort of consistent, but it's certainly not definitive. And the 3rd panel from Mori, there were not coincident wind measurements, so these don't really show any wind dependence directly. There's no way to get that from this figure. It's a normalized velocity difference, and the circles, the red circle and the open circle below it, show sort of an estimate of the cloud of data points in the original figure, and the dots are estimates from the model. And you can see that the upper shear, which is between 5 centimeters and 10 meters in this normalized velocity depiction. Those dots fall within the red circle, so it's sort of in the right place. For the deeper shear between 1 meter and 5 centimeters, it's the dots tend to show a lot more shear, But on the other hand, the velocities, there was a fair amount of mesoscale geostrophic velocities in these that couldn't be removed from this estimate. And so it's not clear the way the normalization was done, so it's not clear. So on the right is probably a better comparison. This is with Fabrice Ardouin's comparison with, I think it's a year-long record of HF radar off the west of France. And the top plotted estimate, or so I've taken these values from the figure in the dark line, or the black line with the X's in it. Those are the observed values of total velocity versus wind speed. And then in the middle panel, the percentage of the wind speed. And in the bottom panel, the angle relative to the wind. And the model estimates are in the blue and the red dashed line. And most of the observations are below 10 meters per second. So in that range, there's some consistency again between the model and the observations. Right about, it crosses the percent line right about 7 meters per second. You see the model shows something closer to 1% for wind speeds below 10 meters per second. This is averaging the model over the upper 1.5 meters, basically. And the angle in that range of sort of 3 to 10 meters per second is also not too far away. At the higher wind speeds, obviously, it diverges quite a bit. There were fewer observations, and so it's not, I don't know what to say. The model could well be wrong. I'm going to skip this. There's an implied correction to the bulk drag coefficient here, and this is maybe relevant mostly in the case where you have a very fine resolution in the vertical, a model with very fine vertical resolution that starts to resolve this wind drift layer. Basically, if you have a wind drift that is 3% of the wind speed, and you reference the relative wind to the actual surface velocity rather than to the sort of nominal 10-meter depth at which surface currents were included to the extent they could be in the core calibration, you end up essentially reducing the drag coefficient by 6% since it's quadratic. And so that's basically what this shows. It gets a little bit less as you get to higher wind speeds in this model because there's less shear between the surface and 10 meters effectively in that case. So this is not saying that drag coefficient is wrong by any means, or that there's scatter, that maybe a little bit of scatter depending on exactly what depth the observed measurements were made at, but it's really more of a bias if you reference to the true surface velocity, and it has this value of roughly 3%, rather than to the 10-meter velocity where the reliable measurements were deemed to be. So I want to come back to this 3% rule for just a moment. So it turns out that if you neglect the waves and you sort of replace the interface by a rigid sheet that transmits the stress, you can get a value you can get an exact prediction from a turbulent universality argument for the surface drift. And it turns out to be close to this 3% value. And in fact, you get something like the 15-degree rotation as well, because the 10-meter wind is rotated to the left of the geostrophic wind, and the anti-symmetry of the implied anti-symmetry of the dimensionless turbulent boundary layers is what gives you the result, and it effectively gives you an interpolation formula between the two free stream velocities where the weights are just the square roots of the respective densities. So I want to look and see in this case with this roughness length especially, and also the wave effect parameter that deviates quite substantially from the sort of nominal assumptions for the atmosphere, how far from this anti-symmetry do these states lie? And so the two top panels on the right are normalized photographs of the atmospheric velocity in the green and the ocean velocity from the model in the blue. Actually, the atmospheric model, the atmospheric wind profile here comes from effectively the same model, but now with the standard use atmospheric roughness length instead. So it maintains that sort of classical structure for any wind speed. And the little dashed green lines show you what the anti-symmetric photograph would be for the ocean velocity. And you can see that the blue lines, which come from the model, are a bit from that. They don't extend quite as far, and they're a bit off in direction for 5 meters per second wind on the left. And they're quite far from it for 15 meters per second wind on the right, where basically the large roughness length and small wave effect parameter nearly truncate the log layer, which is that effectively truncated to nothing, which the log layer is the long straight portion in those photographs where the stress is constant, but the velocity changes rapidly. So the middle panels just show you the same thing in the unnormalized, so the dimensional variables. And if this were symmetric, the point where the two profiles meet would be exactly on that dotted axis line of where v equals 0. So the blue and green circles would lie a little bit up to the right on the dotted line, and that would be the point at which the surface drift is exactly in the direction of the geostrophic wind, so rotated a bit to the right from the 10-meter wind. And the stress photographs are in the bottom panel, and they are actually fairly similar, but they're distorted a bit in depth, effectively, which is you can't see in this photograph formulation. So here's a summary. I don't know how that went in terms of the timing here, but just wanted to emphasize again the motivation here that understanding the near surface wind drift, I think, is important for the retrieval calibration and the physical interpretation of the Doppler scatterometer measurements. And we have a really exciting opportunity here to get global measurements of this variable. And this offers new possibilities for understanding of the ocean that I really look forward to that possibility. And so in this talk, I've tried to put forward a sort of what I think of as a straw man dynamical model of the near surface wind and wind wave drift in this homogeneous equilibrium C case, which I think is relevant. I mean, it's relevant to the extent that the drag coefficient is relevant, and it is. We use it all the time. This sort of estimate should be relatively, it should be possible to come up with a sensible estimate of the profile in a similar way for the upper few meters of the ocean. And so I've argued to use this mass-weighted mean and surface conforming coordinates, and that this captures both the wind and the wind wave drift. And you get a mean momentum balance that has the classical appearance, but a modified meaning. And the turbulence closure here is a wave modified mixing length eddy viscosity. Use the Stokes drift profiles plus the 3% rule to get a nominal calibration, and it shows a log layer near surface shear for low wind speeds with surface velocity within 10 to 20 degrees of the wind, and a more constant near surface shear for higher wind speeds with a surface velocity that's rotated a bit farther from the wind. And at this point, there's been a sort of preliminary comparison with existing observations, but it's certainly not conclusive. So I'll stop there. Thanks very much.
Thank you, Roger. This was great. Questions for Roger? Fabrice has his hand up.
Hi, Roger. Yeah, thanks very much for walking you through the paper. And I think I really appreciate the effort of having a simple model for the surface. There's one thing I've been toying with some time ago, which is source of possible inconsistencies, and that's a question of the mixing and how mixing happens in the presence of waves or not, and what are the timescales of the mixing relative to the timescale of the wave period. So people that have been working on wind wave generation know that problem very well, because it's been plaguing numerical models of wind wave generation for a long time, and so there's all this discussion of this the fact that the mixing happens on a scale which is typically longer than the wave period, and so you shouldn't actually apply the same mixing for the mean flow that you do for the waves. And so I was trying to get a sense of looking then on the water side of things, how much, so if I understand correctly, you actually have this eddy viscosity which is acting both on the total velocity field you get from this Jacobian and all that stuff. And I'm afraid that this eddy viscosity may actually be too large in compared to what we know about swell dissipation rates. That if you actually run swell in your model, it would actually won't propagate very far because it will get dissipated in a very short distance. So I don't know if you've thought about that problem, or if you can comment on that.
Yeah, I guess my perspective on that is that this is intended to be a mean over everything. And so the waves are already gone. So I wouldn't take this viscosity and put it back into a model that has waves. You know, there are a lot of physical aspects of how the circulation actually works that are going into this mean that are very complicated and delicate. And I don't pretend to understand all those. But the idea of this, I think, is the waves have been averaged over already. They're no longer in the flow that you're trying to resolve. In fact, in this simple case, there aren't any horizontal gradients in anything or any temporal gradients. It's just like a bulk drag coefficient in its simple estimate of what the profile is under those equilibrium conditions. But I don't know if that answers the question or not. But I guess that's my perspective on the issue that I think you're raising there.
Okay, well, I think I have to read the paper in more detail and maybe I'll make sense of that. Okay, thanks.
Thanks for the question.
Other questions? Kenneth Hughes has his hand up.
Yeah, hey, Roger. This might be a similar question to what was just asked. Can you pull up that slide that you compared your model to Fabrice's observations?
I can try. Yeah, this one.
Yeah, so I'm kind of, I was kind of surprised that, and I think you were saying that you weren't quite sure the discrepancy beyond 10 meters per second winds in panel A in the top right.
Yep.
But it kind of seems to me intuitive that you would expect things to flatten off, whereas your model showing it almost increasing in steepness with wind speed. Like there must be some kind of thing that saturates with how much, I don't know, energy or momentum you're putting in. Is that fair or?
Yeah, I think the question here is how deeply and how well mixed are the upper few meters under these high wind speed cases in the sense of momentum. So if the eddy viscosity is not large enough for whatever reason in this model, whether it's the wave effect parameter being too small or the roughness length being too small, I think that would bring, you know, if the right calibration is less, you know, a smaller percentage and a greater departure from the wind, then I would expect, you know, you essentially would be moving more and more towards the Ekman flow. But there's a bit of confusion for me here because the observations seem to show a tendency towards more downwind velocity at these higher wind speeds, as well as the lower percentage, which indicates deeper mixing. And I think, I haven't looked at this too closely, but I think it's hard to make the model do those two things, because essentially as you increase the surface eddy viscosity and make it more constant, you're approaching the Ekman layer situation. And so I'd expect to have the smaller percentage at higher wind speed also accompanied by a greater deviation from the downwind. So again, I don't know if that answers your question. Those are some thoughts about this.
Yeah, no, I guess I was thinking mostly in terms of magnitude. I guess it's helpful to think about the angle it's going at the same time. So thanks.
Right. Yeah. So, you know, if the basic dynamics are correct, then it's a question of what the right parameterization is to get the unique velocity field that should be there in this mean description.
Thanks.
And it could be that that eddy viscosity is not the right parameterization. You know, that is a possibility that, you know, that having the waves and the wavy boundary there just really completely changes the physics relative to the rigid boundary. And you can't just sort of fix them up in this way. That's a possibility. Maybe you need a body force directly or something like that. But I don't know. My intuition, for what it's worth, is that it shouldn't change it that much.
Right.
Bia, you've got your hand up.
Yeah, thank you, Roger, for the talk. Just quick comment on your last comment about a body force. So have you considered the contribution of braking to the drift?
Well, you know, it's in there in my mind. I mean, you know, it's all parameterized, whatever this stress is, right? And so it's just a question of what you're trying to fit. And I don't think we have enough data to say what this mean profile is that we're trying to see. So the braking does some sort of transport. I've made an argument that that eddy viscosity at the surface can be interpreted in terms of wave braking, you know, consistently with with sort of an enhanced wave braking dissipation layer. And so, you know, it's sort of in there in a way. On the other hand, you know, of course, the surface conforming coordinates, if you really were to follow each braking wave, that doesn't quite work theoretically anymore. So on the other hand, braking waves generally tend to cover, you know, a fairly small fraction of the sea surface. So maybe it's okay.
All right. Yeah, I'm not sure I agree with the very last point, because you're considering equilibrium seas, so that implicitly implies braking. But yeah,
Yes,
we
but
can
not
talk about
braking
it.
everywhere. I mean, braking all the time somewhere.
Right.
But
Okay. Yeah.
yeah.
Thank you.
Roger, I wanted to ask you, on your final slide, you ended up with your summary statements about different responses one might expect for low winds and high winds. Do you think those are detectable? Would those be detectable from space? What resolution would we need? What accuracy would we need to get it at the distinctions that you're predicting?
You know, I guess I wouldn't be trying to detect those from space in a direct sense. You know, I think this, well, again, Ernesto can comment better than I can, but I think this measurement is going to be what it is.
Mhm.
And the real question is, how do we calibrate and how do we understand it? So
Yeah.
you could imagine taking the measurement and using some knowledge of the wind from the combined measurement and the state and a model like this to infer what the actual true skin surface velocity is, for instance,
Mhm.
which would not be a direct measurement. But if you understood it, you know, you might be able to get a better idea from the measurement of what it actually is. And in a similar way, it should help the effort to calibrate the measurement to understand what you're measuring and what the profile actually is in the upper meter or so over these different wind conditions.
Mhm. And I think the other question I had is that at the very beginning, you started with a set of assumptions that laid out the framework you're going to do, or that set the conditions for the framework that you've analyzed. What happens if you relax those assumptions?
Well, that's a good question. I think the first one to relax, probably from a theoretical point of view, is the assumption of the steady momentum balance.
Mhm.
So if you allow just the linear acceleration terms in there, you can still solve this equation. You know, I think Lewis and Belcher solved a version of that, and I think you and Shin have also solved a version of that.
Mhm.
And arguably, that is still okay if you believe that wind wave equilibrium occurs within a few hours, say. So maybe there's some separation between the inertial timescale and that equilibrium C timescale. And so then you would have something that would say something more about near inertial wave generation, that sort of thing. It would be a little bit more general. That would be the first one that I would try to generalize or relax.
I guess the other question is how important, to match observations, how important is it to start tweaking assumptions?
Well,
Probably takes experimentation.
yeah, good question. I mean, I don't feel that I really know how well this model matches observations yet. You know, there are a lot of observations out there that I haven't yet tried to look at.
Moma, you've got your hand up.
Yeah, hi. My question would be in a similar way. What happens if you think about swell or like non-local generated waves? So that's also one of the assumptions you make in your first slide. It violates the homogeneity assumption a lot. So it will affect wave bank statistics, but also your Stokes drift profiles somehow.
Yeah, sure. There's certainly the question of the disequilibrium of the wave field and the swell. You know, there's going to be some contribution to the Stokes drift from the swell, from a theoretical point of view, at least. And I think there are some observations consistent that this can be seen at times, but the longer waves tend to have you know, a smaller effect on the total drift. But so you could either you know, you could supplement this model with a model of swell and directly take the Stokes drift from that. That's one approach. If you feel it's not destroying the basic physical structure that you're modeling with this kind of model, or maybe it needs a more complete revision to capture that effect.
Thanks. Are there other questions? If not, we'll thank Roger for a really great talk and great discussion. This was very interesting and gave us a lot of food for thought.
Oh, looks like there's a, those are clapped hands. Well, thanks very much. Thanks very much for listening, folks. I appreciate it. All right. See you at the next seminar.
Thanks. And there's no seminar next week, and we'll pick up again in 2 weeks' time.